So now we're going to try to find the formula for the surface area of a sphere. At the moment, all we know how to do is find the volume of a sphere. The volume of a sphere is equal to 4/3 times pi times the radius of that sphere cubed. And somehow we need to get from this formula, which is the only thing we know about spheres, to the formula for surface area. Spoiler alert, the formula for surface area of a sphere is 4 pi r squared. So how do we get from finding out how much stuff can fit inside a sphere to how much stuff can fit around the edge of a sphere? Well, consider this. If we have a sphere, say this golf ball, we can approximate its surface area by wrapping the sphere in a very thin shell, in this case, tinfoil. This sphere is slightly bigger than this sphere. Its radius is bigger by the width of the tinfoil. If we were then to take the foil off of the sphere and lay it flat and smooth it out, what we end up with is a very thin prism. The volume of this prism would be the area of its base times that really, really, really thin height. If we can get the area of the base of this prism, we're going to get a really good approximation for the amount of area it would take to cover this golf ball. If we make this prism infinitely thin, as that thickness goes to 0, then the area of the prism would become the area of the golf ball. So our overall game plan is going to be as follows. First, we're going to find the volume of a slightly, ever so slightly, larger sphere. Next, we're going to subtract the volume of the original sphere. If we have the foil-wrapped golf ball and we subtract the golf ball, all that's left is the volume of the foil. So if we subtract the volume of the original sphere from the slightly larger sphere, that should leave a shell. And then we're going to divide the volume of the shell by its really, really small thickness, leaving the area of the base of the shell. And if we make our thickness small enough, the area of that base of the shell will also be the area that's covering the golf ball. So let's get to it. First, we have to find the volume of a slightly larger sphere. I'm going to define a variable, x. Let x be the super small thickness of the shell. X is the thickness of my foil in this case. Therefore, volume of the slightly bigger sphere, I'll call it V bigger, is going to be 4/3 pi times the radius of my golf ball, or my original sphere, plus this very small, tiny thickness cubed. My original sphere had a radius from its center to its edge. My new sphere is going to have a slightly bigger radius, and the amount that's slightly bigger by is the thickness of the foil, which, remember, we're making super, super tiny. So we have this nasty term here, r plus x cubed, because this whole term is the radius, so this whole term has to be raised to the third power. There are many ways you can do this. If you remember how to expand binomials, go for it. Alternatively, we can always do it the long way. Anything that's cubed is just that base times itself 3 times. So I can always expand this r plus x cubed term into just a whole bunch of r plus x's times each other. I can then use my lovely FOIL and my distribution rules to resolve this into a nice polynomial with none of these weird parentheses in play. So r times r is r squared, r times x is rx, x times r is xr, x times x is x squared. And all of this will have to be multiplied by r plus x. Again, I can go through and do my distributions. I'm going to clean this up a little bit first, because I notice that these two terms are actually the same thing. R times x is the same as x times r, the same way that 2 times 3 is the same as 3 times 2. So I have 2 xr's, and I have an x squared. So I'm going to do the same thing. I'm going to distribute this r, and distribute this x, and then add everything up together. So r squared, so r times r squared is r cubed. R times 2xr is 2xr squared. R times x squared is rx squared. X times r squared is xr squared. X times 2xr is 2x squared r. And x times x squared is x cubed. So this mess is the same as r cubed plus 2r squared x, 3r squared x, because I can combine this term and this term, plus 3rx squared plus x cubed. So the volume of the bigger sphere, the one with the shell, can be expressed as 4/3 pi times this whole mess. Cool. We have found the volume of a slightly larger sphere. Now, in order to get the shell, the tinfoil part, we're going to subtract the volume of the original sphere, the golf ball. Well, the volume of my original sphere was just 4/3 pi r cubed. So V bigger minus V original equals 4/3 pi times this mess minus 4/3 pi times the original radius cubed, the volume of the original golf ball. I'm going to go ahead and distribute this term to get rid of these parentheses. Parentheses make everything more difficult. Should be a pi term in all those guys. We end up with something that looks like this. 4/3 pi r cubed plus 4 pi times the radius squared x plus 4 pi times the radius times x squared plus 4/3 pi x cubed minus the original 4/3 pi r cubed. I notice that these terms are going to cancel each other out. And so I'm left with this formula for the volume of a shell. 4 pi r squared x plus 4 pi r x squared plus 4/3 pi x cubed. Cool. We've done our subtraction. We have figured out the volume of the original sphere, leaving only the shell. This is V shell. Our last step, we want to take that shell and divide it by its thickness. We're approximating it as a prism. So if we can divide it by its height, that should leave its area, the area of its base. So if we have v shell over the height. Remember, the height of my prism is going to be the thickness of the foil. This is the base of my prism. This is the height of my prism. So we're going to be dividing everything by x, the thickness of the foil. 4 pi r squared x plus 4 pi r x squared plus 4/3 pi x cubed all over x. The volume of the shell divided by its thickness is going to be the surface area of the sphere. 4 pi r squared x divided by x is 4 pi r squared. 4 pi r x squared divided by x is 4 pi r x. And 4/3 pi x cubed divided by x is 4/3 pi x squared. All right, but this is not this. The first term is the same, but then we have all this gobbledygook over here. And here's where math gets really clever, a tool that you're going to be learning a lot more about in calculus. Our shell has a thickness. But as long as it has some kind of a thickness to it, the area of the top and the area of the bottom aren't going to be a perfect match for the area of the sphere. You can think of the shell as being slightly curved, and the top part is going to be slightly longer than the bottom part. As a result, as long as there is a thickness, those two sides won't perfectly match up. It's technically not a prism. But as we get closer and closer to having zero thickness, as we make this thinner and thinner and thinner and thinner, it gets closer to being a perfect prism. In math, we represent this as taking the limit of a function as x goes to 0. We ask ourselves, what happens to this function as x basically becomes 0, as it becomes infinitesimally close to 0? Well, the first term remains the same because it has no x component to it. It doesn't care. But look about these two terms. As x gets really super close to 0, they become irrelevant. The difference between a true prism and what is actually happening here goes away. Multiplying this 4 pi r term by 0.00000000000000000000000000001 makes it irrelevant and it goes away. It basically becomes 0. Same with this term here. So even though we can't find the surface area of the sphere directly, we can say as this shell gets infinitely thin, the surface area will converge on this value. If we make our shells thinner and thinner and thinner and thinner, their area looks more and more like 4 pi r squared. So in theory, if we had a shell of 0 thickness, this would be a perfect representation of its surface area. So in conclusion, we first found the volume of a slightly bigger sphere, whose radius was bigger by a value of x. We then subtracted the volume of the original sphere from the bigger one, leaving only the volume of the shell. Finally, we took that shell and we divided it by its really tiny thickness to leave just the area of the base of that shell, which is the surface area of the sphere. We then broke out some clever calculus tricks to ask ourselves what happens to the surface area as that shell becomes infinitely thin. The thinner that shell is, the better an approximation it's going to be for the surface area of the sphere. If we take it all the way to 0, then the formula for surface area of a sphere becomes that. And that is how you derive the formula for surface area of a sphere from its volume.